Video we're going to understand microcontroller. We're going to understand LPC2129 microcontroller in this video, and this LPC2129 microcontroller is a ARM7 based microcontroller. LPC2129 is a ARM7 based microcontroller, and it is a 32-bit microcontroller. We will understand complete architecture of this LPC2129 microcontroller, what is available in this microcontroller, what are the peripherals available, and what are the applications of those peripherals. We will understand. So let's start the video, guys. So right now what you are seeing on the screen, this is your LPC2129 microcontroller, which is based on ARM. Guys, this LPC2129 microcontroller is a 64-bit IC. Right now what I'm going to highlight here, so this is the IC of your LPC2129 microcontroller. If you see the pins here, so pin number 1 to pin number 64. So there are totally 64 pins available, and each 64 pins are having multiple functions that we will discuss later in the coming videos. So directly I can say here it is a IC, and which is having totally 64 pins in this microcontroller, which is manufactured from NXP, founded by Philips. You can see here, so this is the company's name, NXP, and this is my controller name, LPC2129. And how many pins are available? Totally 64 pins. So in detail we will discuss in this video. So guys, so in this microcontroller I told you already, which is the ARM7 based processor. So where is the ARM7? We have already discussed about the ARM7 processor. So we are using inside this controller ARM7 processor, and the complete name of this processor is ARM7 TDMI-S. So I just want to recall your previous videos, guys. ARM7 TDMI and S. We are using 32-bit processor, which is of ARM7 TDMI. So ARM7 is a series. T stands for thumb mode, D stands for debug mode, M stands for multiplier, and I stands for in-circuit emulation, ICE mode, and S stands for synthesizable version. So this is the full form of your ARM7 TDMI processor. We have already discussed in the nomenclature of your ARM processor. Okay, so this ARM processor is able to operate at maximum of 60 megahertz. So it is going to be operated at 60 megahertz. So maximum frequency of this ARM7 TDMI processor is to be operated at 60 megahertz, and this can be programmed. This frequency can be reduced by using PLL. We have circuitry called as PLL. PLL stands for phase locked loop. Using this phase locked loop, we can able to reduce the system frequency with the help of PLL. So thus this PLL you can view here. So this is my circuit which is able to reduce the clock frequency of your CPU. Using PLL we can change the frequency. So in detail we will see later. Then how much we are connecting external crystal oscillator? So we are connecting external crystal oscillator of 12 megahertz. So crystal frequency we are using of 12 megahertz. Externally we are using 12 megahertz crystal oscillator. Using this external 12 megahertz, we are creating a new frequency with the help of PLL. So in detail we will discuss later. Yes. So apart from this, we are using one additional circuit that is called as AMBA bus. So we are using one additional circuit called as AMBA. AMBA stands for Advanced Microprocessor or Microcontroller Architecture. Advanced Microcontroller Architecture. Advanced Microcontroller Bus Architecture it is called as. AMBA stands for Advanced Microcontroller Bus Architecture. So what it does, sir? So it does the connectivity between your processor and peripherals. So in this circuit or in this diagram, I can divide complete microcontroller into two things. One as a system block and one as a peripheral block. So you can see red color what right now I'm highlighting. This is called as system block. So this is my system block or system bus I can call. System block, or system bus I will call. And here what you are seeing in the blue color, so this is called as peripheral block. I will call as P block. So P block stands for peripheral block. So in this peripheral block, all peripherals are connected. What are the peripherals? We already know the peripherals like timer, pulse width modulation, general purpose. So in detail we will discuss all these things in the next session. So just as of now you can understand in this way, AMBA bus stands for advanced microcontroller bus architecture. So this is going to interconnect your system, nothing but your CPU. So this is my CPU and I'm going to interconnect my CPU and my peripherals. So this is the advantage of AMBA bus architecture, and AMBA bus it is responsible to interconnect your CPU and your peripheral. And at the same time, your AMBA bus is going to divide the clock for your peripherals and to the CPU. So let us assume my CPU is running at 60 megahertz. My CPU is running at 60 megahertz. This is called a C clock. So in our technical term, we will call a C clock. The C clock is going to be operated at 60 megahertz, and we have one more clock that is called as a P clock. So we will I'll represent here. So we have one more thing called as a P clock. So P clock stands for peripheral clock. This peripheral clock is equal to 1 by 4 times of 1 by 4 times of C clock. So 1 by 4 times of C clock is nothing but, so this is going to be 15 megahertz. So I can say here my peripherals are operating at 15 megahertz and my CPU blocks, nothing but system blocks, are operating at 60 megahertz. So this we should keep in the mind. What is the role of AMBA bus architecture? So AMBA bus architecture, it is able to connect your CPU and peripherals, and also it is able to divide the frequency. So this is the main functionality of your AMBA bus. Okay. Apart from this AMBA bus, so we have RAM and ROM here. So RAM, here I want to highlight. So we have a built-in RAM which is of SRAM. We have totally 16 kilobyte. So in our microcontroller, so we have 16 KB of SRAM. 16 KB of SRAM we have. We are going to use this SRAM to store the data temporarily. Okay, and we have other also flash RAM. We have a flash in our microcontroller. This flash is going to be 256 KB. So this is highlighted here, the flash control unit, and totally in our microcontroller we have 256 kilobyte. LPC2129 is having 256 KB of flash. So we are going to store the program in this flash memory. Okay. So apart from this flash, we can see here something called as APB divider. So this is a divider. So here this is called as divider I will call. So this divider is going to divide your CPU clock to peripheral clock. This is responsible for dividing the clock, higher clock to lower clock, with the help of APB divider or VPB divider. Coming to the peripheral parts, so peripherals. So first I will talk about timers. You can see here we have timers. We have two timers. Both are 32-bit. I will explain in the next slide. We have pulse width modulation PWM unit. So we have totally 6 channels pulse width modulation circuits are available. So then when we talk about a GPIO, so we have GPIO of 2 ports, port 0 and port 1, both are 32-bit. And we have 10-bit ADC, analog to digital converter, which is having a totally 4 number of channels with this ADC. And we have interrupt unit. So we have external interrupt unit, and also we have vector interrupt controller. So we have 2 supports. One is a vector interrupt support also we have, and we have external interrupt support also. After this, we have peripheral called as RTC, real-time clock, which is going to give you a real-time clock. So you know already with this real-time clock we can generate alarm, or we can monitor any device with RTC. Okay. A real-time clock is also called as RTC in short form. And we have Watchdog timer. So what is the role of Watchdog timer? Watchdog timer is going to protect your microcontroller when it enters into the infinite loop or error condition. That is the help of your Watchdog timer. And we have protocols. We have totally 4 protocols in our protocol support in our microcontroller. The first of all I want to highlight about UART. So UART stands for Universal Asynchronous Receiver and Transmitter. We have two UARTs, UART 0 and UART 1. Using these two UARTs we can able to communicate with other device. And we have second protocol called as SPI. SPI stands for Serial Peripheral Interface. Here also I can find the two SPI interfaces, SPI 0 and SPI 1. And it is a 4 wide protocol, and there are 4 wides. What all that I'll explain in the next slide. And third protocol stands for I2C, Inter-Integrated Circuit. This is a 2-wired protocol. So this is also a protocol which is a serial communication based protocol, and we are able to communicate using this I2C protocol. Then finally I have CAN. So in my microcontroller we have a automotive based CAN protocol. CAN stands for Control Area Network. So this control area network, it is able to communicate a device to device widely used in automobiles. So in detail we will see in the upcoming videos. Okay, so this is a general description of about this microcontroller. We will explore little more things about this architecture in the upcoming slides. Yes. So in this microcontroller, so we will start one by one. So guys, this microcontroller is a LQFP. LQFP stands for Low Profile Quad Flat Package. So that means in the previous diagram we have seen already. So what do you mean by LQFP, Low Profile Quad Flat Package? So quad flat package means in all 4 directions I can find the port pins. LQFP stands for Low Profile Quad Flat Package. All 4 directions I can find the pins. So you can see here I have pins here, I have pins here, I have pins here, I have pins here, and I have pins here. So this is called as quad flat package, and it's a low profile. Why? It is taking only 3.3 volts. In order to operate properly, my microcontroller will take 3.3 volts. It's a low profile quad flat package. Okay, I hope this is clear to all now. So I'll move to the controller features. Yes, LQFP stands for low profile quad flat package. Number of pins I already told, it is 64 pins. In my microcontroller I have 64 pins. Inside this processor or inside this microcontroller I told already, we have ARM7 TDMI processor. This is my ARM7 TDMI processor, which is able to operate at 60 megahertz. So this CPU clock can be operated or it can be programmed using PLL. So I already told in the previous explanation, we have separate one special circuit called as PLL. So this PLL stands for phase locked loop. Using this PLL I can able to change my CPU frequency. Using this PLL I am able to change my CPU frequency. How? In detail we will see later. We have SRAM and we have flash. This thing already I told you. We have SRAM, totally 16 kilobyte of SRAM I have, and totally 256 kilobyte of flash I have in my microcontroller. We have 10-bit ADC. So I told you already. So in the previous explanation I told you we have 10-bit ADC. This is my ADC. So we have 10-bit ADC and I can connect up to 4 different channels. We have 2 timers. So this is my timer block. So we have totally 2 timers, both are 32-bit. So we have timer 0 and timer 1. So both are 32-bit. Using this I can develop my applications. We have pulse width modulation circuit. So in this pulse width modulation circuit, totally I can have totally 6 outputs. So 6 outputs we have PWM. PWM stands for pulse width modulation. So this pulse width modulation is used to control the motors, or it is used to control any device where you can use in the applications, embedded system applications. So we have RTC, we have Watchdog timer also. So we have RTC. So this RTC we already told you. RTC stands for real time clock. So using this RTC I can get the real time, current date I can get with the help of RTC. Watchdog timer. So Watchdog timer, we are using this Watchdog timer in order to protect your microcontroller when it is entering into infinite loop, or uh, when it is entering into the error conditions. So in order to avoid, or in order to reset a microcontroller when it is entering into the infinite loop, we will utilize Watchdog timer. So we have vector interrupt support. So with the help of vector interrupt support, we're able to configure our interrupts, and we can able to generate interrupt service routine, and we can execute ISR, interrupt service routine. So we have four protocols, guys. I already told in the previous video. So we have UART. UART stands for Universal Asynchronous Receiver and Transmitter. Using this, I can able to communicate, and this is a two-wire protocol. So UART will be having a two wires, a transmitter and receiver. Using these two wires, I'm able to communicate using UART. So that UART part you can see here in this block. Okay, this is my UART. So we have two UARTs using this, and I'm able to communicate. The second one is I2C. I2C stands for Inter-Integrated Circuit. I2C stands for Inter-Integrated Circuit, and it is again a two-wire protocol, and two wires are called as SCL and SDA. SCL stands for serial clock, SDA stands for serial data. Using these two lines, I am able to communicate device to device. We have two SPIs. So SPI, you can see SPI 0 and SPI 1. So we have two SPIs. SPI stands for serial peripheral interface, and it is a four-wire protocol. Okay. So what are the four wires? I'm going to write it here. So one is called system clock, CK, and second one is called as MOSI, stands for MOSI. MOSI stands for master out slave input, and we have something called as MISO, stands for MISO, master and slave out, and finally SS. SS stands for slave selection. So SPI is a four-wire protocol. What are the four wires? SEK stands for system clock, and MOSI stands for master out slave in, and MISO stands for master in slave out, and SS stands for slave selection. In detail, you're going to study later. So what about I2C? So in the I2C, I can find only two lines. One is called as SDA and one is called as SCL. SDA stands for serial data and SCL stands for serial clock. So SDA, serial data, which is responsible to carry the data, and SCL stands for clock line, and it is responsible to generate the clock. And in case of UART, we have transmitter, TX and RX pin. So UART is a two-wire protocol again. So UART will be having two lines, TX and RX. TX for transmission, RX for receiving. So like that, micro protocols are having various application pins. The last one is called as CAN. CAN stands for Control Area Network, and using this CAN, I'm going to transmit and receive the data again. So CAN again, it's a two-wire protocol. So we'll be having two wires called as CAN H and CAN L. So I'll be having two wires, CAN H and CAN L. Using these two wires, I'm going to communicate in the embedded system applications. So CAN stands for Control Area Network. So this is a brief explanation of your LPC2129 microcontroller. Okay. So now we will study. I hope this is clear to all. Okay. So now I'll move to the